Welcome to the Leap Australia tutorial for Pyfluent watertight meshing for FSAE. This tutorial will cover basic geometry preparation, but mostly focus on the setup of the Pyfluent scripts and how they function. Geometry preparation is one of the most important factors that influence meshing success and results quality. Taking the time in geometry preparation to fix areas that may cause the meshing to fail will save countless hours when trying to generate a successful mesh for the first time. An example geometry file has been provided with this tutorial which has already been prepared, but it is important to note some of the common causes for failed meshes. Correcting these issues prior to meshing will save time down the line. So one of the first common issues for failed meshes is the trailing edges of airfoils. So it's important to make sure that there's no sharp trailing edges that end at infinitesimal points. Otherwise you're going to have bad mesh cells along the trailing edges, which result in very low quality meshes, as well as just failed meshing. So it's important to try and cut the trailing edge of any airfoils flat in your CAD generation stage. And if mesh failures still occur on certain elements, the pull command within ANSYS Spaceclaim can be used to further cut that short. So like that for an example. So it's just important to check that on all of the airfoils. As you can see here, these have all been cut flat already in the example geometry that you've been provided. A similar issue that can arise is infinitesimal points, like on diffuser strakes, for example. So if this geometry over here didn't extend down past that and it ended at an infinitesimal point like that, that can create meshing issues down there. So the easiest fix for that is just to again use the pull command to extrude that face down and just ensure there's no infinitesimal points of intersection within the geometry. Another area of common issues that can arise for meshing is thin geometries or gaps. So for example, if the strake had a thickness that was smaller than the minimum element size used in meshing, then that can cause meshing issues. So the easiest fix for this is, again, to use the pull command just to widen that strake and ensure that there's no thin geometries present. The same could be said about that. A similar thing could be on this end plate, for example. And so just keep an eye out for those. Another issue that can arise is with the wheel to ground fillets. Sometimes people choose not to have these fillets. Sometimes people do. One important factor to remember with these is the best way to ensure mesh success with these fillets is to just make sure that the fillet radius is larger than the minimum element size used for meshing. That way you won't have any meshing issues. Otherwise you can reduce the mesh element size. But the radii of these can be changed just by, again, using the pull command to change that radius like that. Further issues is overcoarse mesh sizing. So that's going to get come up when you get to your mesh generation stage and you choose your mesh element sizes. That will be explored later in the script. But choosing mesh element sizes that are far too large for geometry can cause the mesh to fail because ANSYS can't apply a surface mesh to a geometry when that element size is too big for the geometry. And so in order to generate a successful mesh, you're going to have to take the RAM penalty and the mesh size penalty and just run a finer mesh. One of the final common issues that arise is missed faces in name selections. So over here in Spaceclaim, you've got your groups tab, which is where you create your name selections. So that's everything from enclosure, faces, all to front wheel, helmets, rear wing, front wing, etc. And missing faces, like if you were to miss that top face on the end plate of the side aero element stack over there, for example, can sometimes lead to meshes failing, especially when trying to apply boundary layers. And so it's just important that when creating the name selections, try your best to get every single name selection included or every single face included in the name selection. So if I select all of the front wing elements, name selections here, and then I hide them, there shouldn't be any elements or faces left over anywhere here. That's just an easy and simple way to check. Just a few more notes on geometry preparation. Is the repair and prepare tabs appear in Spaceclaim. These tools are useful in looking for errors within your geometry. And so I generally like to work from left to right on these tabs, just checking for things like gaps, missing faces, split edges, etc. Work my way through, and then move to the Prepare tab, where I then check for any interference, short edges, and bad faces are generally the key ones on this tab. And then once that's completed, I'll create the enclosure using that command over there. One important thing to remember with these is that sometimes ANSYS, or at least Spaceclaim, can't fix certain geometry issues. So like if it finds a split edge that it cannot repair. That's not to say that your geometry is unmeshable. Generally try, if you have one or two errors that still persist, don't write off the geometry, try and mesh it, see what happens, and then just keep that in mind. If the geometry does fail, then you can go back and go, okay, well, I had a split edge or an extra edge that I couldn't get rid of that in that region that might be causing that issue. The last factor of geometry preparation is the creation of named selections and the naming conventions used to create these named selections. Name selections created during geometry preparation are incredibly important, as they will be referenced by the script specifically when applying mesh sizings to the different name selections, as well as, for example, setting rotating wheels within the solution setup stage. Feel free to continue using the name conventions outlined in the following slides or develop your own. The most important part is to keep them consistent. Given this tutorial uses a simplified geometry file with fewer named selections, the naming conventions shown in the following slides are limited. However, more detailed naming conventions for more complex simulations are shown at the top of the Pyfluent meshing script. The naming conventions start with the named selections for the enclosure. So this includes the inlet face, outlet face, symmetry face, and ground face, and the walls, as well as the body of influences with the respective named selections shown in the table. The naming conventions also include general components such as the chassis or bodywork, helmet, wheels, wheel contact patches, and can be expanded to include suspension as is shown in the top of the Pyfluent script. However, these are not included in the slides for the simplified geometry. The following naming conventions are used for the aerodynamic components. So for example, the front wing is shortened to FW, side aero is shortened to SA, rear wing is shortened to RW, and the undertray is shortened to UT. And then the name selection is suffixed by what element or what component it is. So the main plane of the front wing, for example, would be FWE1, the second element would be FWE2, the second element of the side aero would be SAE2, and so on for the rear wing. And then the undertray itself is split into the undertray bottom surface, which is the UT, and then the undertray top surface, which is the UT top. Before going through the Pyfluent script itself, it's important to get Pyfluent installed on the computer, and so the following slide will detail how to do this. In order to install Pyfluent, it is required to have both Fluent and Python installed on the computer on which you are trying to install Pyfluent. The install can be completed by opening a command prompt window and typing in pip install Ansys Fluent core. For more information, please refer to the video linked in the slide. This will detail how to install Pyfluent itself and any of the specific requirements that need to be completed in order to successfully install Pyfluent. Before we get into meshing using Pyfluent scripts, it is important to go through watertight meshing itself first, understand how watertight meshing is completed, how it functions, and then translate that into the Pyfluent script. Fluent's new watertight meshing workflow is designed to help guide the user through the meshing process. Understanding how this workflow works and the steps involved will make understanding the Pyfluent script itself far easier. The workflow is divided into separate steps, and the Pyfluent script is split into sections of code which each relate to the separate steps shown in the image on the right. For more information on meshing within Fluent without Pyfluent scripting, please refer to the video linked. Understanding how the meshing is completed manually will help with understanding how the script functions and therefore problem solving down the line if anything is to go wrong or not work correctly. Now that we understand how the watertight meshing workflow works, we can now look at how the Pyfluent script itself achieves the same output from the watertight meshing workflow. So looking at the script itself, this over here and this big section over here would be a workflow section that relates directly with the workflow section of the watertight meshing workflow. These blocks over here, like that one there, for bodies of influence, and that one over there for curvature sizings, would be workflow subtasks that relate to the different types of sizings that you can apply within the sizings workflow section, and then that over there would relate to a block, and that over there would relate to a block. So if you would like to add another body of influence, for example, you can simply select this entire block and then copy and paste to add the new block in, and then change what is required. So here's an example of a to-do comment, just reminding you to change the name of your body of influence if you are using a different naming convention. If you're using the same naming convention, then everything should translate over automatically. There should be a few more here reminding you to change certain name selections, or making sure that geometry descriptions are correct, for example, and so on. Then there should be a few more warning comments within the script, like this one over here, just reminding you that depending on how you change, say for example this global multiplier variable, it may affect the success of generating a mesh, and so like values too large or too small here would either cause the mesh to fail, or if the value is too small, it's going to take a very long time to mesh. So the script summarizes all of the mesh element sizings and other sizings used within the script into a single location for easy editing. This involves sizings like the global multiplier here, which will change the mesh sizing of the entire mesh with a single value. So it will just multiply all the separate sizings by the value specified there. So specifying this value over here as 1 will allow you to mesh it with the default mesh sizings of the script. It then includes your body of influence sizings for the large and small bodies of influence. So if you would like to change the default value for that, that value over there can be changed. It then includes the curvature sizings for aerodynamic components, general components, which involves like chassis, roll hoop, helmets, etc., as well as the wheels, the wheel curvature controls. So these values can be changed as required based on your meshing strategies. And then it also includes values such as the improve surface mesh limits for the improved surface mesh task, further controls for the global mesh generation or surface mesh generation, boundary layer specifications, so boundary layer first layer heights, the number of layers, the transition ratio, the boundary layer method itself, the volume mesh settings, as well as the important one here is the mesh improve quality. It's important to remember not to set this value too high, as it can degrade other metrics of the mesh. So generally a value around 0.1 or 0.15 is ideal. Maximum I would go is about 0.2 on mesh improve quality. When simulating new geometries using the script, it is important to update sections of the script to ensure the meshing and simulation is successful. The last and probably most important variables within the global sizing section is the file path of the save directory as well as the geometry file name. If these aren't specified correctly, then ANSYS isn't going to be able to read in the correct geometry file or find the correct working directory. And so it's advised to create a working folder where you would like all of the generated files saved. That just makes, obviously, data organization easier. And then ensure that your geometry file is correct. If using Windows 11, you can copy the file path just by right-clicking and saying copy as path. The one issue with that is it then puts the file path within double quotation marks, so something like this, which is going to cause an issue within the script. So if that is the case, just remember to remove the double quotes that are added, and just remember not to delete that R in front over there. And then the mesh save name, you can save as anything that you like. Over here, it's just saved as full car mesh. The important thing to remember is that when using the setup script later, you're going to have to specify this mesh name so that the setup script can read in the mesh. And so it's just going to be, you have to make sure that it is kept consistent between the two scripts. Cool. The next section is the settings of the Fluent instance that will be opened when the script is run. This includes things like the Fluent version, the type of simulation, so either 2D or 3D, the precision, and then one of the most important ones here is processor count. So currently here it's set as 24. I've got 32 cores in this machine. But generally you will have to change the processor count value over here to what is allowed by your license that you receive, as well as what your computer is capable of. So for testing purposes, when running this example geometry, this will run through perfectly fine and quickly on a processor count of 6. Another important one is the show GUI option, which is set as true. This just means that when the script is run, a Fluent window will open and you will be able to see the script automatically complete all of the tasks, and you'll be able to see all the progress of the mesh. That's just useful for debugging, seeing how everything is going. If you don't want that GUI to open, then that can be set to false, and then no GUI will open. But it's nice to be able to see what the script is doing. The next section is the import geometry task that will simply just import the Spaceclaim geometry specified up here into the Fluent instance so that meshing can begin. The next section is all of the local sizings. So it is the local sizings are first applied to the bodies of influence. So you've got the large body of influence over here, you've got the small body of influence over here, and it will just use the global sizings specified up here and apply those sizings to the actual specified geometry. The same thing will happen with the curvature local sizings for aerodynamic components, general components, and the wheels, and that happens all over here. So it's important to remember to change the name selections labels over here depending on what geometries or components you have within your geometry. So for the provided geometry, that includes like bodywork and default. For the general curvature settings, and then it includes the front wing, all of those elements, the rear wing, the side arrow, and the under tray for the aerodynamic components, and then the front wheel, the rear wheel, and then the contact patch fillets for the wheels. The next task is then to generate the surface mesh using all of the created sizings within this workflow section over here. And that will generate the surface mesh with the surface mesh settings specified in the global settings above. Once a successful surface mesh is generated, the improved surface mesh task is then used to fix any bad cells that were generated from very difficult geometries to mesh within the geometry itself. And so this task over here will aim to help and improve and repair any bad cells and improve the quality of the surface mesh that was generated. The next workflow section is to describe the geometry. This is the section that tells Fluent what part of the geometry is what type of material, for example. So it tells Fluent that you have only fluid regions within this geometry and no voids. Or you can say that you've got fluid regions with voids, and obviously you might then want to mesh those voids, but in our case of here, we don't want to mesh those voids. So for that reason, we set wall to internal as no, as well as invoke shared topology as no. We're not interested in the voids, so we don't want to waste any mesh elements on meshing inside those voids. The next section is to update the boundaries. Not much has to happen over here. One important thing to note is that if the wheels are not cut by the ground plane using wheel fillets or connected to the chassis via suspension, then ANSYS might still try to mesh those voids. And so in the next section, which is the update region section, if that is the case, these triple quotes over here can be removed to specify those regions as dead. So in other words, tell Fluent not to mesh them. Generally though, if there is suspension modeled, which is a lot more accurate or realistic, or the wheels are cut by the ground plane with wheel fillets, then that shouldn't be an issue. And so this block is not required. And so all that has to happen is it just has to execute the update regions section. The next one after that is boundary layers. So this uses the global sizing specified above to tell Fluent which name selections to apply boundary layers to, and obviously all the boundary layer settings themselves, so like the boundary layer first layer height, the number of layers, the type of boundary layer method, etc. And then once the boundary layers have been applied to those different name selections, the volume mesh can then be generated. This just specifies what type of cell type you would like. So it could be tetrahedral, hex-core, or polyhedra. The final section is the improve volume mesh task, which will use the mesh improve quality specified earlier to hopefully try and improve the quality of the volume mesh. It is, as mentioned earlier, it's important to try and keep the mesh improve quality target between 0.1 and 0.2, ideally around 0.15 for the best results, as anything higher than 0.2 will degrade other mesh metrics. Once the improve volume mesh task is completed, the mesh is then checked to ensure that a valid mesh has been generated, so there's no negative volumes, for example. And then once the mesh has been successfully checked, it is then saved to be used in the setup process. The following is a time-lapse of the script running through, showing how the script works through each of the workflow sections to generate a successful mesh at the end. So over here we can see the final generated mesh generated by the meshing script, and it can be seen over here that you've got the small body of influence over there, then the large body of influence roughly sits about over there. You just can't tell much of a size difference because of the global multiplier of 3 that was used, and then you've got the full enclosure mesh over there. And then we can look in and take a look at the surface mesh on the bodywork over here. This is a polyhex core mesh, so fairly uniform cells. You can see the capture curvature refinement there around the leading edge of the side arrow element. Same thing with the rear wing element. The inflation layers can also be seen over there on each of the rear wing elements, as well as in the diffuser and on the bodywork as well. Same thing on the front wing main plane. And then another feature of Fluent is you can insert clipping planes. We can change which direction it is in. Do it in Y, and then we can draw the cell layer and move the area. So there we can see the difference in cell size between the small body of influence, the large body of influence, and the enclosure. And then if we go a little bit further, we'll be able to see the actual volume cells of the generated mesh, including all the boundary layers within the mesh. And if we go out a little bit more, we'll be able to see the volume mesh generated around the side arrow in that region. And we can see there's a bit of stair stepping on the third element, on the second element of the side arrow stack, which is likely due to the trailing edge geometry. And so if we want to reduce that stair stepping there, which will definitely increase results accuracy when the simulation is run, then the trailing edge geometry there needs to be pulled a bit more to increase the trailing edge thickness. The same thing can be seen on the second element of the front wing over there. The stair stepping is also likely due to the large element sizes used, given the global multiplier was set as 3 for this demonstration. So setting it to 1 should also correct that issue. The separate setup script will be explored in the next tutorial and will detail the setup process and begin the simulation. Thank you for watching and see you in the next tutorial.